Good morning once again. So now we would be discussing the third part of 7.1 lecture. So this is lecture number 7.1. A and B, these two parts are done. So this is 7.1c. In 7.1c, we will try to estimate theta W or grinding temperature. So that's what we are going to do. So this is an analytical solution. This solution was proposed by Jaeger in 1942. So long back. And he was not an engineer, he was a mathematician, and he was not even bothered about grinding. So he simply provided a solution for a particular scenario. What is that scenario? There is a semi-infinite body which is moving in this direction with velocity Vw. There is a heat source on the top of it. Heat flask which is entering the job is Qw, or the semi-infinite body. The length of the semi-infinite body is 2L. So for that he said theta. This theta is not temperature, please note it down. This is rise in temperature. This is rise in temperature. So if this rise is 200 degree and if the ambient temperature is 25, the actual temperature would be 225. So this is delta. So rise in temperature is given by this complex equation. This equation you need not have to remember, and second of all, this time it is all open book test, so you can always go back to your note and consult them. This equation I would not derive. Those who are interested, they can go to Jaeger's original paper and have a look at it. So what does it depend on? If Q increases, temperature increases, which is understandable, and other things are not so straightforward. Say for example, the role of V is not so straightforward. Definitely if V increases, the temperature will go down. I'll give you an example. Say for example, don't do it and please do not do it. Say for example, a candle is burning, and if you have to put your finger through the flame, if you do it very fast, nothing would happen to you. So there, if you increase your velocity, this V by 2, V to the power half and V will cancel out, but you will get an expression where theta is a function of kind of this. So if you go put your finger through the heat source very fast, nothing would happen to your finger. So here also, if the V is very high, not VW, V is very high, nothing would happen. Now the question is, this is a semi-infinite body. This is a uniform heat flask. So how much of it is comparable to grinding? So this is my grinding. This is the length of the grinding, length of the job. How much is it? No idea. There is no, you do not know. But if you take 150 millimeter, that is a representative length. With what would you compare it to say that this length is sufficiently large? You can compare it with LC. This is 3 millimeter. So with respect to LC, this is 50 times larger. You can compare it with respect to downfeed. Downfeed is say 30 micron, and in that particular case, it is much more larger than A. You can compare it with respect to HM, which is 1 micron. With respect to HM, LW is sufficiently large. Second one is, what is its width? Width can be anything, but despite that, we have solved quite a lot of problem with a BW value of 10 millimeter. Even if it is 10 millimeter, this 10 millimeter is sufficiently longer than the characteristics length in grinding, which is HM. So for all practical purpose, as far as the semi-infinite thing is concerned, that means the job is sufficiently long with respect to the length of the heat source. These things are comparable. We are not making lot of mistake. What about this one, which is uniform heat flask? This we are making a I should not say mistake, but we are making a departure. What is that departure? This is the chip load, and as because this is the chip load, HI is constantly increasing. As HI is increasing, FTI, that is instantaneous force coming onto a grid, that would also increase. If that increases, then definitely you can understand QW would not be uniform. So there would be some amount of non-uniformity, and because of that there would be some departure from Jaeger's solution. But despite that, Jaeger's solution is a very neat analytical solution that we can use in case of grinding. And if we use it in case of grinding, how the situation would develop, let us see. So theta would remain theta. This will remain 3.543. 2 alpha would become alpha W, that is thermal diffusivity of the workpiece. Q would becomes QW, then pi by KW into V would become VW into VW divided by 2 alpha, and this L is nothing but L by 2. So this will become LC by 2, and whole thing would have a power of 0.5. So if I divide this number by pi, I get 1.13 into 2 alpha W QW divided by KW VW, and this side it becomes VW to the power 0.5 LC to the power 0.5. This 2 becomes 4, so it is square root of 4 and alpha W to the power half. So this square root of 4, this one will cancel out. This will become 1.13 into this LC and this VW, and this combination will give you this one. This QW will stay here, and now we are stuck with this member, and this member. What is alpha? Alpha W is nothing but KW by rho W into CW. This is specific heat, this is density, this is thermal conductivity. So this half will come here. So in the numerator you would have KW to the power half, in the denominator you would have rho W to the power half and CW to the power half. And there was always, once again, this KW was in the denominator, so which will come here. So this we will write it as beta W, where beta W is nothing but square root of KW into CW into rho W, where this is the density of the workpiece, this is the density of the workpiece, this is the specific heat, and this is the thermal conductivity. Okay, so beta W is a new thermal property term that we have introduced. So what we are getting is this particular equation by analyzing from Jaeger's solution to this particular solution. So can I estimate grinding temperature? Let us rewrite this equation here. LC is contact length, is decided by downfeed and diameter of the workpiece. So we can estimate that. VW is the work speed, so that is also known to us. Beta W is nothing but root over thermal conductivity of the workpiece, specific heat of the workpiece, and density of the workpiece. If you are grinding a particular work material, chances are its properties would be known to you, so beta W you would be able to calculate, and that is multiplied by 1.13. So what is the only thing which is not so straightforward? The only thing which is not so straightforward is this particular term, because we know QT, which is FT into Vs divided by LC into BW, but we do not yet know this. How it can be related to QT? It is related by RW, the apportionment coefficient which was introduced in the earlier lecture. So if there is any way of estimating RW, then we would be able to calculate how much is QW. With this, we will stop and then we will go for how to calculate RW using two different approaches. One approach would be has been proposed by Malkin, the book of Malkin which we are using. The same member, same person has proposed a particular method that we will be using, and another one is a much more analytical approach. Malkin's proposal is much more empirical and there is a bit more analytical approach. Both of them we will try to use, we will discuss them and we will solve numerical problem. And once we do that, then how to estimate grinding temperature in dry grinding using conventional wheel, that particular objective of our course would be fulfilled. Thank you so much. We will meet again shortly.